thank you very much for this kind introduction and, of course, for the invitation. It's really a beautiful place here, and I would love to have more time to go a little bit around. But we have all many duties, and but the next time I would like to spend much more time here. So today I'm talking about Memristor enhanced control of a bio-inspired humanoid robot, and my talk is dedicated to address, let's say, a point which is coming more and more up. Also, it's not very new. The idea is to overcome the limits posed by von Neumann architectures, where you have on one side the processors, on the other side you have the memory, then you have a bus, and this takes a lot of time, so this is the bottleneck. And there are many investigations now focusing directly on the idea to have embedded memory connected to processing units, but possibly when we are looking on memristors, we can make use of these memristors not only considering them as a non-volatile memory, but use the dynamic behavior of these memristors to perform analog computing as well. And today my presentation is aiming to give, let's say, a first approach in order to enhance the movement control of a robot. Therefore, I have my outline is I start with a short, some 1 or 2 slides for the motivation. Then I will introduce the bio-inspired humanoid robot, Meyer. Meyer has been manufactured and developed by Manfred Hill from the Neurorobotics Lab in Berlin. And then after introducing 2 analog computing paradigms for the movement control of the robot, I would like to show how we can make use of the Memristor to enhance these movement control. Let me firstly mention my co-authors. This is Alon Ascoli, who is sitting here in the audience and giving the last presentation of this session. Then Dominik Baumann, who made some calculations in his diploma thesis. Manfred Hill was constructing and developing Meyer. He's leading the Neurorobotics Research Laboratory in Berlin. And we have a huge support from Leon Schua in circuit theory enhancing our work. So when we are looking for devices for memory and computing, then we can see that on one side we have the development of neuromorphic devices, for example, phase change memory, in order to create new forms of computation. Here is one example for this. And on the other side, also looking on neuromorphic networks, we can also make use of organic electronics. But this is not only a topic for academics. We can observe that huge companies are investigating more and more money into that business. And we might all know the recent announcement of Hewlett-Packard introducing a new memory-driven computing structure, which is called the machine. The machine has been developed over the years, and recently the machine has been presented at the World Expo, Computer Expo at the CeBIT in Germany, in Hanover, and they showed the first functional architecture, which is bringing together memory elements and processing units. This is the underlying idea of this new type of computing structure. But is this a new idea? No, it is not a new idea, because when we are looking on analog computing, and I have one example for you, which is coming from the year 1999, so this is from the Electronic Times. In 10 years before 1999, in 1988, 1989, the paradigm of cellular neural networks has been invented by Leon Schua and his student. And the idea is to have an array, a cellular array of dynamic elements. Each element is talking to the other, to its neighboring elements, and the dynamic behavior of these structures will be used to solve problems of information processing. So this is analog, mixed digital analog computing. So you can program these type of computers which are coming from these ideas digitally, but you use the dynamic behavior in order to solve problems. And when we look on a single cell of these networks, then we can see here we have the nucleus. This is the computing unit of a CNN cell. But directly at the computing unit, you have in the CNN universal machine, these are computing structures resulting from these ideas. You have local analog memory. So you have directly at each cell, you have your memory. And this is what we have, an array of distributed computing elements and with embedded memory. And this idea, this led to computing structures with stored programmability and resulting in vision systems. For example, here we have one vision system coming from a Spanish group, from Angel Rodriguez Vasquez, who is a fully sensor processor system, has a fully computational capability, and you can process images with this structure with frame rates in the kilohertz range. So you have frame rates of 20,000 kilohertz for certain applications, also in industrial applications. In Germany, there are different companies who are making use of these high-speed sensor processor systems. And recently, Toshiba took over this technology, fabricating the so-called smart photo sensor chip, SPSO2, which is in principle implementing these ideas. So analog computing is of high interest, and the Memristor can exactly give an enhancement in this direction, because the Memristor is not only a binary element having a high resistance or low resistance, but there is something in between, depending, of course, on the material. But depending on the material, you have a nonlinear state equation, and making use of the dynamic behavior of this nonlinear state equation, which possibly generate chaotic behavior, wave propagation, or something else, you can create highly efficient analog computing. Today in my presentation, I would like to give a first approach to analog computing implemented in a bio-inspired robot. This robot is called Meyer. Meyer, as I already mentioned, has been manufactured and developed by Manfred Hild in the Neuro Robotics Research Lab in Berlin. It consists of 6 body parts. So you have head, torso, 2 arms, and 2 legs. So it's in principle a modular system. And having a length of 1.25 meters and a mass of 16 kilograms, which is equivalent to the average size of an 8-year-old child. So let me show you a small video in order to introduce.
This is Project Alir, created by Dr. Luke Steels.
It's not
this
working.
This you see here is named Meyer. Meyer is 1.25 meters tall and weighs only 16 grams. Notice Meyer moving his arms and interacting. Scientists at the Neuro Robotics Research Laboratory believe that true artificial intelligence can only be achieved by allowing machines to develop and evolve like young children do. The focus of the research project is to explore how complex grammatical systems and behaviors can emerge in populations of robotic agents. Here you can see 2 Meyer robots talking to each other. This is their own created language.
Okay, well, oh, is that the word it just learned?
Yes, yes, yes.
So since we are limited in time, let me stop the video here. Since we are not focusing on cognitive abilities of Meyer, we are looking today on the control movement. This is not a classical control system which is implemented on Meyer. It's a system which depends on different paradigms. One very simple paradigms. One of these paradigms is the so-called go against the force paradigm. A very simple idea. Assume that you have, for the sake of simplicity, assume that we have a pendulum which represents a limb of a body. And you have a motor which drives this pendulum. And the idea is of the go against the force paradigm to drive, the motor should drive the pendulum against the force, which is in case here the gravitation force. So this is the underlying idea, and we have considered a DC motor model. The motor model is given here, so you have the armature voltage VA, the armature node A, then we have a second circuit in order to generate a certain flux in order to drive the motor. The idea is to use the motor as not only as an actuator, but also as a sensor in this setup. So the motor will be considered as a sensor and actuator, and having this idea, we implement an iterative behavior. The idea is to bring up the pendulum into the upright position, so to bring up the limb into the upright position, which is equivalent when you have a zero-valued angle gamma. We are looking on this angle here, and this is one of our control parameters. So we have different phases. So we start with a sense phase. In the sense phase, look here on the flow diagram, the limb or the pendulum is falling down. This falling down leads to a voltage generated by the motor. This voltage will be integrated. So here we have an integrator. And we consider a negative sign in order to create finally a movement against this direction caused by the gravitation force. So we, in a certain time period, in the sense phase, we are integrating the voltage, and then afterwards we apply the motor voltage, the result of the integrator, using this result as the voltage applied to the armature node of the motor in order to drive the motor in a drive phase. And then we go back to the sense phase, and then we have different sense and drive phases finally in order to reach the upright position of the limb. So, and this will be continued. Let me show you a small implementation of our lab where we, in order to show that this principle is working. So you see the slow movement, and then afterward, at the end, this tiny pendulum reaches the upright position, and it's very stable in this upright position. Here on the next slide, we see different cycles of these sense and drive phases. Let's start with a drive phase. Here we have the angular frequency. So we start in a moment when the pendulum is falling down. So you have a negative angular frequency, and then you drive the motor. That means you increase the angular frequency for direction of positive values. And this can be observed when you look on the angle, gamma, which is drawn in figure D. Then you see first falling down, then you increase the angle, but then you drive the motor more and more into the upright direction. And then you have a sense phase and a drive phase and so on. The issue with this go against the force paradigm is that it's rather slow. Finally, this is it's reliably working, but it's slow. You need for certain parameter values, the whole time period which is necessary is 18 seconds. And on the other side, when you look on the integrated absolute value of the armature voltage as a measure of the energy which is necessary to move the pendulum or the limb upright into the upright position, you can say that this is energy inefficient. But how can you improve this idea? The very simple approach is that think about why should we iterate in this way into the upright position. We may start with a huge kick, bring up the pendulum close to the upright position, let the pendulum fly, and then try to stabilize it around the upright position. And this brings us to the second paradigm which has been implemented, which is called the kick-fly-catch paradigm. And this paradigm is based on a mathematical principle from Russian mathematician Pontryagin, who is saying if you would like to have an optimal control of a pendulum, then you have to apply for a certain time the maximum voltage which drives the motor, and then afterwards, in the rest of the period, you can use a minimum voltage. This is a very simple result of this paradigm, maximum principle. So we implemented, first we have a kick phase. In the kick phase, we drive the motor with a maximum voltage, which is provided by your setup, for a certain time period, which is given by T star. The goal is to reach, to have a significant decrease of the angle, but keeps above 0. Then we have a second phase, the fly phase. In the fly phase, the limb moves up freely, but in this phase, we have to monitor the movement of the pendulum. Because when you look, for example, again on the limb, and you're coming close to the upright position, you are slowing down, and possibly the velocity, the angular velocity is changing its direction because it's falling back. Then you can find this when you see that the angular frequency or the voltage generated from the motor is based on this effect. Or you are too fast, you're coming over the top position, you're slowing down and then increasing again. So during the fly period, you monitor these, looking for these typical movements, and if they appear, then you start the catch phase, which is in principle the application of the old go against the force paradigm in order to bring the pendulum to the upright position and stabilize there. The issue is here that you need to determine the duration of the kick phase, and therefore you need to estimate the energy which is necessary to reach in the kick phase this, let's say, considerable movement close to the upright position. Okay, this can be done in the following way. We have implemented a second integrator, so we perform a double integration. We use let's say the output of the first integrator, and we perform the second integration, which the result is given here, in order to firstly to apply in the initialization the go against the force paradigm. We perform the second integration, so we get an estimate of the energy which is necessary to come to the upright position, and then we can make use of this in the kick phase based on the principle of Pontryagin. When we take for the control voltage the maximum voltage, then we can solve this equation and for the time t star which is necessary to drive the motor with a maximum voltage into the upright position. The Memristor can, let's say, enhance this movement because the memristorance, when you perform the second integration, by taking a memristor into account, the non-volatility of the memristor will memorize this upright movement, and when you perform iteratively more upright movements, then you will change the memristorance during the run. Okay, so we have the full story we have here on the flow diagram. The variables are given in the Laplace domain. Here we have the angular frequency. This part here represents the torque generated by the motor. This torque is coming from the gravitation force. Here this coefficient B stands for the friction of the motor. Finally, we have here the angular frequency. Then taking this value, we can calculate the voltage generated by the motor. Then we have three switches, 1, 2, and 3. Here in this setup, we are looking for the kick phase, where the first integrator, which is implemented here, is switched off, but you have this part here. This part is giving the estimated value for the time which is necessary, T star, in the kick phase. So we can close in the kick phase the switch number 3 to apply the maximum voltage to the armature node of the motor. Then in the second phase, in the fly phase, we open S3, but we are closing S2 to this part, and this part of the circuit is dedicated to monitor the movement of during the fly phase, in order to find these points when you need to start with the go against the force paradigm in the catch phase. So, and the catch phase is represented here. So we have here, we are closing S2 in order to perform the integration of the output. And then finally, in the drive phase, we apply the integrated value directly to the motor. So these are the different phases. And let me show you an example where these ideas, these two paradigms have been implemented in the lag of Mayon. So this is a full autonomous system. This, it will be switched on now. And then the whole circuit is working. Oh, 4 minutes. Oh, I have to speed up. The whole circuit is working against the gravitation force. Okay, this is rather stable in this position. Sorry, let's go on because I'm running out of time here. And we have implemented these ideas with two different Memristor models. One is an emulated model based on titanium dioxide linear drift model from Hewlett-Packard. And the other one is a model which has been developed for a fabricated device of the company NOM. And it's roughly speaking, it's based on two Schottky diodes between two electrodes, and then you have conductive states with different conductivity. So you have two states, A and B, and you have a certain number of conductive switches being in these two states, and these conductive switches can jump between these two states. This is the underlying idea of this NOM Memristor model. So N total gives the number of conductive switches. Then the total current of this Memristor consists of these metastable, the contribution of these metastable states, and the contribution coming from the Schottky diodes, which their current contribution is given here in this equation. The current contribution coming from the metastable state is given by Ohm's-based law. So we have the memductance here, according to the number of switches in state A and those in state B, and a change which is coming from these change of the conductive switches. And these changes, which are shown here, are random numbers. So you have a random model here, and these random numbers, practically the change of this conductive switches follows a normal distribution. So let me briefly show the result of the integration of the Memristor. As I said, we need firstly an initialization phase. We initialized the algorithm with a load mass of 10 gram. Then we apply the go against the force paradigm in order to estimate the kick phase duration. And we can see that by applying the classical go against the force paradigm, we reach the upright position. But here we can see the memristance follows this behavior, and the result memorized in the Memristor can be used to estimate the kick phase duration. Now we're changing the load mass. These results have been calculated for the ideal Memristor model. Let me mention this part. Now we're changing the structure of our limb by increasing the mass, so the load mass to 25, 30, and 35 grams, just as an example. That means we have, in the initialization phase, we have estimated the kick phase duration, and we did it for 10 grams. So the estimated value gives not enough time to come close to the upright position, and this can be seen here. So we are here, at this point, we start with the go against the force paradigm, which finally iterates to the upright position. But during the application of the go against the force paradigm, the memristance is changing. And by applying in the second application, we have already a faster, let's say, convergence to the upright position, still changing memristance values. And finally, after 4 iterations to 6 iterations, we have a very nice performance that almost at 1 second, we have let's say, the limb brought the limb into the upright position. And the memristance is not changing anymore. And here we see the performance of it now for a different Memristor model. To give you another example, where we can see that the angle here starting in the kick phase, we have reached the upright position almost in 1 second, and this procedure is much more energy efficient as the classical go against the force paradigm. 1 minute. For the no-M Memristor device, the problem is it was very sensitive, so we cannot apply a continuous voltage to the device. We have to change it to a pulse-based excitation of the device and incorporating a threshold in order to get this result. So, since my time is running out, so this is the first approach, the first idea to make use of such structures, to use a very simple circuit. It's a very simple circuit in order to perform a movement control. And we are looking for more, let's say, complicated structures in order to endow the robot with more abilities in the future. Let me mention at the end of my presentation the birth of the Showa Memristor Center. This was in last year at the 5th Memristor Symposium. The Memristor Center is an expert center bringing together world-leading experts in Memristor research in order to establish a comprehensive theoretical foundation on Memristors for the creation of new innovative circuits, new computing structures, and finally to organize joint projects, organization of workshops and publications. And I would be very happy if you are interested in our activities. Thank you very much.